Imagine a machine smaller than a kitchen oven, sitting inside a steel cylinder colder than deep space, that just solved a problem no computer on Earth could ever solve. Not in a year, not in a century, not in the entire remaining lifespan of the universe as we understand it. In December 2024, deep inside a Google research lab in Santa Barbara, a chip the size of a coin did exactly that. It was called Willow, and what it calculated in under 5 minutes would have taken the fastest supercomputer on the planet longer than the universe itself has existed. Researchers didn't celebrate right away. According to people close to the project, the first reaction inside the lab wasn't excitement, it was silence. Because before anyone could understand what Willow had proven, they first had to confront a stranger question. If a machine can perform a calculation that would take longer than the age of the universe to verify by any conventional means, where exactly did that calculation actually happen? This is the story of a chip that was supposed to prove a theory. Instead, it cracked open a debate that scientists had spent decades trying to avoid. A debate about parallel universes, about the limits of what reality can compute, and about whether we have just built a machine that quietly reaches outside the world we can see. Before we go further, we need to understand what came before Willow. Because this story didn't begin in 2024. It began with a much smaller, much more fragile machine, and a claim that nearly tore the scientific community apart. In October 2019, Google's quantum research division announced something extraordinary. A chip called Sycamore, built from 53 qubits, had reportedly performed a calculation in 200 seconds that the world's most powerful classical supercomputer, IBM's Summit, would need approximately 10,000 years to complete. Google called it quantum supremacy. The term itself was provocative. It suggested that, for the first time in computing history, a quantum processor had done something a classical computer functionally could not. The backlash was immediate. IBM disputed the claim within days, arguing that with smarter classical algorithms and enough storage, the same calculation could be completed in roughly 2.5 days, not 10,000 years. Researchers at universities around the world began publishing competing papers. Some defended Sycamore, others tore it apart. The scientific community split into camps, and for a while it looked like quantum supremacy might become one of those claims that fades quietly into controversy and gets forgotten. But Google didn't walk away. Behind the scenes, in a research facility built specifically for chip fabrication in Santa Barbara, engineers spent the next 5 years trying to answer the one criticism that actually mattered. Sycamore was fast, but it was also fragile. Quantum bits, or qubits, are notoriously unstable. They lose their information through a process called decoherence, and the more qubits you add to a system, the more errors accumulate. For years, this had been considered one of the fundamental walls blocking quantum computing from ever becoming truly useful. Add more qubits, get more power, but also get more chaos. That wall is what Willow was built to break. Researchers at Google Quantum AI, led by physicist Hartmut Neven, spent years refining a new approach to error correction. The idea itself wasn't new. Physicists had theorized for decades that if you could group physical qubits together into something called a logical qubit and scale that grouping correctly, errors should decrease rather than increase. The theory had a name, below threshold scaling, but no one had ever demonstrated it experimentally. Not once, not anywhere in the world, until Willow. In findings published in the journal Nature in 2024, the Google Quantum AI team reported something that physicists had been chasing since the 1990s. As they increased the number of physical qubits in each logical qubit grouping, from a grid of 3 by 3 to 5 by 5 to 7 by 7, the error rate didn't increase. It dropped exponentially. Each time they scaled up the system, the chip became more reliable, not less. Getting there required more than clever mathematics. It required an entirely new physical facility. Google built a dedicated chip fabrication plant specifically for quantum processors, a controlled environment where engineers could manufacture superconducting circuits with a level of precision that previous generations of quantum hardware simply could not achieve. Every qubit on Willow had to be tuned individually, its resonant frequency calibrated with extraordinary precision, because even microscopic manufacturing imperfections can introduce the kind of noise that destroys a quantum calculation before it finishes. The chip itself operates inside a dilution refrigerator, cooled to roughly 15 millikelvin, a temperature colder than the depths of interstellar space, colder than anywhere naturally occurring anywhere in the known universe. At that temperature, thermal vibrations that would otherwise scramble delicate quantum states are suppressed almost completely. This is where most documentaries would tell you the hard part was over. It wasn't. Because solving the error correction problem was only step one. The real test was still ahead, and it would force the team to confront something far stranger than circuitry. The next phase of the experiment was something called random circuit sampling, often abbreviated as RCS. Think of it as a kind of benchmark, a way to push a quantum processor through a calculation so absurdly complex that classical computers simply cannot keep pace. The 105-qubit Willow chip was given one of these benchmark tasks, and here is the number that stopped researchers in their tracks. Willow completed the calculation in under 5 minutes. To verify that result using one of the fastest existing supercomputers, a machine called Frontier, housed at Oak Ridge National Laboratory, would require roughly 10 septillion years. 10 followed by 24 zeros. For context, the universe itself is approximately 8 billion years old. The number researchers were looking at wasn't just larger than the age of the universe. It was larger by a factor that the human mind struggles to even visualize, but that wasn't the strangest part. Hartmut Neven, the physicist leading the project, made a comment in the aftermath of the discovery that ignited international attention far beyond the usual circles of quantum physics researchers. He suggested that the result lends credibility to an idea first proposed by physicist David Deutsch decades earlier. The idea is this: if a calculation takes place that would require more computational steps than could possibly occur within the observable universe in the time and space available, then perhaps that computation isn't happening only here. Perhaps it is happening across many parallel branches of reality simultaneously, branches predicted by something physicists call the many worlds interpretation of quantum mechanics. Neven described the feeling of watching Willow complete its task this way. The result, he said, lends credence to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse, a notion first put forth by David Deutsch. Let that settle for a moment. One of the lead researchers behind one of the most significant quantum computing breakthroughs in history was suggesting, publicly, that the machine his team built might be borrowing computational power from realities outside our own. Researchers weren't prepared for how quickly this idea would spread, or how divided the response would become. To understand why a single physicist's comment could ignite this much controversy, you have to understand the culture of the field he comes from. Quantum computing research is, by nature, cautious. Careers are built and destroyed on the back of claims that later proved difficult to verify. After the 2019 Sycamore controversy, in which IBM publicly challenged Google's quantum supremacy claim within days of its announcement, the entire field became noticeably more careful about language. Papers were hedged. Press releases were reviewed by committees of physicists specifically trained to avoid overstating results. So when one of the field's most senior researchers stood in front of cameras and used the word multiverse without qualification, people inside the industry noticed immediately. This wasn't a junior scientist getting carried away. This was someone who had spent more than a decade building toward exactly this moment, choosing his words in public, on the record, with his own name and reputation attached. That detail matters more than it might first appear. Scientists who have spent their careers being cautious do not suddenly abandon that caution without reason. Something about what Willow produced moved Neven enough to risk a controversial public statement, knowing full well how it would be received by skeptics within his own field. Some physicists pushed back hard. Scott Aronson, a theoretical computer scientist at the University of Texas at Austin and one of the most prominent voices in quantum computing skepticism, has repeatedly cautioned against the multiverse framing. He has argued that while Willow's results are a genuine and important technical achievement, describing the chip as evidence of parallel universes is, in his words, more poetic than scientific. The math behind quantum computing, he and others argue, can be fully explained using standard quantum mechanics without ever invoking other universes. The multiverse interpretation isn't required to explain why the chip works. It is one possible philosophical lens layered on top of results that can be described in far more conservative terms. So who is right? This is where the story stops being simple. To understand the disagreement, you have to understand what quantum superposition actually is, stripped of metaphor. A classical bit, the kind inside your phone or laptop, can only be a 0 or a 1 at any given moment. A qubit is different. Until it is measured, a qubit exists in something called superposition, a state where it is, in a sense, exploring multiple possibilities simultaneously. When you link many qubits together, the number of possible states the system can represent grows exponentially. A chip with just 105 qubits doesn't represent 105 possibilities. It represents 2 to the power of 105 simultaneous configurations. That number is larger than the estimated number of atoms in the observable universe. This is the heart of the disturbance. Somewhere, somehow, in those microseconds before Willow's qubits collapsed into a final measured answer, the chip was processing a number of configurations that physically could not fit inside our universe if you tried to represent each one using a single physical particle. There isn't enough matter in the cosmos to do it the old-fashioned way. Standard quantum mechanics explains this through mathematics, through probability amplitudes and wave functions, without requiring you to believe other universes exist. But the many worlds interpretation offers an alternative explanation, one first proposed by physicist Hugh Everett in 1957 and later expanded by David Deutsch. In this interpretation, every possible outcome of a quantum event actually happens, just in branching, separate realities that we cannot perceive or access. Under this lens, a quantum computer doesn't simulate multiple possibilities. It genuinely computes across multiple branching universes, and the answer that reaches us is essentially borrowed from a vast, hidden computational network running in parallel just outside the one we experience. Then, something unexpected happened. As the story spread through scientific media and into mainstream coverage, researchers outside Google's team began revisiting old data, old experiments, old unresolved questions about what quantum computers are actually doing when they outperform classical machines by such staggering margins. And the deeper people looked, the more it became clear that this wasn't really a new question at all. It was an old, uncomfortable question that the scientific community had managed to avoid confronting directly until a chip became powerful enough to make ignoring it impossible. Here's where the story becomes difficult to ignore, even for skeptics. Independent verification matters enormously in science, and Willow's results did not exist in a vacuum. The Nature paper detailing the below-threshold error correction breakthrough underwent peer review, a process where outside experts scrutinize methodology before publication. Researchers from institutions outside Google, familiar with the broader landscape of quantum error correction research, have generally regarded the error correction milestone itself, the demonstration that scaling up logical qubits reduces errors exponentially, as a legitimate and important achievement, regardless of how one interprets the multiverse commentary that followed it. This matters because it tells us something important about how to read this story responsibly. There are two separate claims tangled together here, and they deserve to be pulled apart. The first claim is technical and well supported. Google's Willow chip demonstrated, for the first time experimentally, below-threshold quantum error correction at scale. It performed a benchmark calculation in minutes that would take existing classical supercomputers a length of time vastly exceeding the age of the universe. These are measurable, peer-reviewed, replicable claims about a physical device. The second claim is interpretive and philosophical. The idea that this performance proves computation is occurring in parallel universes is a theory, one interpretation among several competing interpretations of quantum mechanics that have been debated by physicists for nearly 70 years, without resolution. The many worlds interpretation is taken seriously by a meaningful portion of the physics community, but it is not the only interpretation, and it is not proven. Other respected interpretations, including the Copenhagen interpretation and pilot wave theory, explain the same mathematics without requiring parallel realities at all. But the real mystery had only just begun, because even setting aside the multiverse debate entirely, Willow raises questions that are unsettling enough on their own. If a machine can reliably perform calculations that exceed, by unimaginable margins, what is computationally possible using all the matter and time available in our observable universe, what does that tell us about the nature of information itself? What does it tell us about the boundary between what is real and what is merely mathematically describable? Quantum mechanics has always lived in this uncomfortable space ever since the early 20th century, when physicists like Niels Bohr and Albert Einstein argued for years over what quantum theory actually meant about reality. Einstein never fully accepted the strangeness of quantum mechanics. He famously resisted the idea that the universe operated on probability rather than certainty, expressing his discomfort with the now famous remark that God does not play dice with the universe. Bohr, along with most of the physics community that followed him, came to accept that on the smallest scales, reality genuinely does behave probabilistically, and that observation itself seems to play a strange, active role in determining outcomes. Willow doesn't resolve that century-old argument. If anything, it makes it more urgent. It is worth remembering just how strange this debate has always been, even before any quantum computer existed. In 1935, Einstein, working alongside physicists Boris Podolsky and Nathan Rosen, published a paper attempting to demonstrate that quantum mechanics was incomplete, that there had to be some deeper, hidden layer of reality that would eventually restore certainty to physics. The paper described what we now call entanglement, a phenomenon where two particles become linked in such a way that measuring one instantly affects the state of the other, regardless of the distance separating them. Einstein found this so unsettling, he referred to it as spooky action at a distance. He believed it pointed to a flaw in the theory, not a feature of reality. Decades later, in the 1960s, physicist John Stuart Bell devised a way to actually test whether Einstein or Bohr had been right. Experiments based on Bell's theorem, conducted over the following decades by physicists, including Alain Aspect, John Clauser, and Anton Zeilinger, who would later share the 2022 Nobel Prize in Physics for this work, repeatedly confirmed that entanglement is real, and that no hidden classical layer of certainty exists beneath it. Einstein, it turned out, had been wrong about this particular point, despite being arguably the greatest physicist of the 20th century. The universe, at its smallest scales, genuinely does behave in ways that defy ordinary intuition about cause, effect, and locality. Willow is, in many ways, the descendant of that very experiment. Every qubit on the chip relies on entanglement to function, weaving fragile threads of connected quantum states across the processor. The same spooky phenomenon that troubled Einstein nearly a century ago is the literal engine driving a machine that just outperformed every classical supercomputer on the planet by a margin too large to meaningfully express in ordinary numbers. And this is where things get disturbing in a different way, a way that has less to do with parallel universes and more to do with what comes next on Earth. Quantum computing of this caliber has implications well beyond academic debate. Encryption systems that protect global banking, government communications, and personal data rely on mathematical problems that are, for classical computers, essentially unsolvable within a practical time frame. Quantum computers, if they reach sufficient scale and stability, threaten to make many of these encryption methods obsolete. Researchers at institutions including MIT and Stanford have spent years developing what is known as post-quantum cryptography, encryption methods designed to withstand attacks from quantum machines precisely because they saw a moment like this coming. Willow is not yet powerful enough or stable enough to break modern encryption. Experts are clear about that. The chip excels at a very specific, somewhat abstract benchmark task, random circuit sampling, which was chosen specifically because it plays to a quantum processor's strengths. It is not yet equivalent to running the kind of large-scale, error-tolerant algorithms, such as Shor's algorithm, that would be needed to crack widely used encryption standards. But the gap between where quantum computing stands today and where it is heading is closing faster than many experts predicted even 5 years ago. Google has stated that its roadmap aims toward a 1 million qubit, fully error-corrected quantum computer within the coming years. The below-threshold breakthrough demonstrated by Willow is, according to the research team, the single most important obstacle standing between today's experimental chips and that future machine. And Google is not alone in this race. IBM has pursued its own path toward fault-tolerant quantum computing, with processors like Condor and a roadmap aiming at thousands of qubits within the decade. Researchers in China, including teams associated with the University of Science and Technology of China, have published their own claims of quantum advantage using photonic processors, approaching the problem from an entirely different physical architecture. Universities and national laboratories across Europe, including efforts tied to research institutions in the Netherlands and Germany, are racing to develop competing error correction techniques. What makes Willow's announcement different isn't that Google is the only group working on this problem. It's that Willow appears to be the first publicly verified demonstration that the central theoretical promise of a quantum error correction, the idea that scaling up could reduce errors rather than multiply them, actually holds up under laboratory conditions. Every competing lab in this race is now working to replicate or surpass that single result. Then researchers turn to a different kind of question, one less about cryptography and more about consciousness itself. Some physicists and philosophers have long speculated about connections between quantum mechanics and the nature of conscious observation, though this remains one of the most contested and least empirically supported corners of the field. The idea that observation collapses a quantum system from a state of superposition into a single definite outcome has occasionally been stretched by some into claims about consciousness shaping reality at a fundamental level. It's important to be direct here. Mainstream physics does not endorse the idea that human consciousness is required to collapse a wave function, and most physicists actively reject this framing as a misunderstanding of the measurement problem. But the discomfort it generates is part of why a result like Willow's strikes such a deep nerve. We built a machine that performs as though it has access to computational resources beyond our universe's apparent capacity, and we still do not have full agreement, after a century of quantum theory, on what observation and measurement actually mean at the deepest level of reality. What came next changed the tone of the public conversation entirely. Major science outlets, including coverage referencing work published in Nature and statements from the Google Quantum AI team, began framing Willow not just as an engineering milestone, but as a genuine philosophical inflection point. Newsweek, Life Science, and other outlets ran headlines invoking the multiverse directly, drawing massive public attention to a result that, in raw technical terms, was about error correction rates and benchmark timing. The gap between the sober, peer-reviewed paper and the explosive public narrative around it became its own kind of case study in how a real scientific achievement can become entangled with speculation the moment it touches a question as old and unresolved as the nature of reality itself. This is where we have to be honest about what we know and what we don't. We know the below-threshold error correction result is real, peer-reviewed, and represents a genuine breakthrough that the quantum computing field has pursued for decades. We know the random circuit sampling benchmark was completed by the 105-qubit Willow chip in a time frame that would be functionally impossible to replicate using classical supercomputing, even accounting for years of future improvements in classical algorithms, an objection that, fairly, did partially undermine the original 2019 Sycamore claims. We know that Hartmut Neven publicly connected these results to the many worlds interpretation of quantum mechanics, a legitimate, decades-old theory taken seriously by a portion of the physics community. We also know that prominent physicists, including Scott Aaronson, have pushed back against treating this as proof of anything beyond standard quantum mechanics. What we don't know, and may never know with certainty, is which interpretation of quantum mechanics is actually correct. Whether reality genuinely branches into countless parallel versions of itself every time a quantum event occurs, with entire universes splitting off in directions we will never perceive, or whether the strange power of quantum computers can be fully explained without ever needing other universes at all, remains one of the most profound open questions in modern physics. It has remained open since Hugh Everett first proposed it in 1957, doctoral research that was so controversial at the time that Everett reportedly left academic physics altogether shortly afterward, frustrated by the field's resistance to his ideas. He would not live to see his theory taken seriously by a meaningful portion of the physics establishment. He died in 1982, decades before chips like Willow would force a new generation of researchers to reckon with the question he raised. There is something quietly haunting about that timeline. A physicist proposes an idea so unsettling that it costs him his career path within mainstream academia. He dies without recognition. And nearly 70 years later, a coin-sized chip cooled to a temperature colder than the depths of interstellar space completes a calculation so vast that the lead researcher on the project finds himself, almost involuntarily, reaching for Everett's discredited theory as the only framework that makes intuitive sense of what just happened. But the deepest implication of Willow isn't really about parallel universes at all. It's about the limits of human intuition when confronted with results that operate on scales we were never built to comprehend. The human brain evolved to track predators across savannas, to count days and seasons, to navigate social relationships in small groups. It did not evolve to intuitively grasp numbers like 2 to the power of 105, or to comfortably hold the concept that the device on a lab bench in Santa Barbara may have, in some sense, briefly touched computational resources that exceed everything physically present in the observable universe. This is where the story arrives, at its final and most uncomfortable question. If our most advanced instruments are now producing results that strain not just our current technology, but our fundamental frameworks for understanding reality, what happens as these machines continue to scale? Google's stated roadmap moves from Willow's 105 qubits toward systems with 1 million qubits or more, fully error-corrected, genuinely useful for real-world problems in medicine, materials science, and cryptography. Each step up that ladder doesn't just mean faster computers. Based on what Willow has already demonstrated, it may mean confronting the multiverse question again and again with greater and greater computational evidence behind it, whether or not the broader physics community ever reaches consensus on what that evidence actually means. Researchers at Google have been careful, in their published work, to frame the multiverse commentary as an interpretation, not a proven conclusion. The Nature paper itself focuses on the measurable falsifiable claims, the error rates, the scaling behavior, the benchmark timing. That caution is appropriate, and it is worth respecting. Extraordinary claims deserve extraordinary evidence, and the claim that we have built a machine that reaches into parallel universes is about as extraordinary as claims get. Science, at its best, resists the temptation to leap toward the most dramatic explanation before quieter, more conservative ones have been fully exhausted. But caution in the laboratory doesn't erase the unease that lingers afterward, because even the most conservative, most defensible explanation of Willow's results is still strange, almost beyond belief. Even without invoking other universes, we are left with a machine that performed a calculation in under 5 minutes that classical computation, using every resource available to humanity, could not replicate before the heat death of every star currently burning in the night sky. That fact alone, stripped of all multiverse language, stripped of all speculation, is enough to make you put down whatever you're holding and sit with it for a moment. Somewhere in a sealed cryostat in Santa Barbara, cooled to a fraction of a degree above absolute zero, colder than the empty space between galaxies, 105 fragile loops of superconducting circuitry held a calculation no human mind, no classical machine, and perhaps no single universe could ever produce on its own. Whether that calculation reached across the boundaries of reality as we understand it, or whether it simply revealed how much more vast and strange the rules of our own single universe truly are, remains unanswered. Maybe it always will. What we do know is this. 67 years after a young physicist proposed a theory so disturbing it ended his career, a chip the size of a fingernail forced the scientific world to ask his question again. this time with data behind it instead of just mathematics. And somewhere between the peer-reviewed certainty of an error correction breakthrough and the unproven, haunting possibility of parallel worlds, we are left standing at the edge of something we built ourselves and still do not fully understand. Perhaps that has always been the real story of human discovery. Not the moment we find an answer, but the moment our own creations show us how much larger the question really was all along. Consider, for a moment, what it actually means to build something you cannot fully explain. Throughout history, humans have occasionally created tools that outran the theories meant to describe them. Steam engines were running factories before thermodynamics fully explained why they worked. Early electrical experiments lit cities before physicists agreed on what electricity actually was at a fundamental level. In each case, the technology arrived first, and understanding followed slowly, sometimes generations later, built piece by researchers willing to sit with uncertainty rather than rush toward false comfort. Willow may belong to that same lineage. A machine running, functioning, producing verifiable, repeatable, peer-reviewed results, while the deepest question about what it is actually doing, whether it is calculating within the boundaries of a single universe or somehow drawing on a vastly larger computational landscape, remains genuinely scientifically unresolved. That is not a flaw in the research. It is, in many ways, the most honest possible outcome. Science does not always hand us clean answers wrapped in certainty. Sometimes it hands us a working machine and a question mark and asks us to hold both at once. What happens next will likely unfold slowly, the way most real scientific progress does, far from the dramatic pace of headlines and documentary narration. More chips will be built. More qubits will be added. Independent labs around the world will attempt to replicate Willow's below-threshold error correction results under their own conditions, in their own facilities, with their own scrutiny. If the results hold, and many researchers expect they will, the conversation will shift from whether quantum error correction can scale to how quickly it can be scaled, and what kind of problems these machines will eventually be trusted to solve. Drug discovery, materials science, climate modeling, cryptography, both the kind that breaks and the kind built to resist breaking. Each of these fields is watching this small, frozen chip in Santa Barbara with a level of attention usually reserved for far louder breakthroughs. But somewhere underneath all of that practical promise, the stranger question will remain, quietly unresolved, the way the best questions in science always do. Did Willow simply reveal how much computational richness already exists within the single universe we inhabit, hidden in mathematical structures too vast for the human mind to intuitively grasp? Or did it, even briefly, even in some way we do not yet have the language to properly describe, reach beyond it? Maybe one day a future experiment will answer that question definitively, the way Bell's theorem finally settled the argument between Einstein and Bohr decades after both men were gone. Or maybe this is simply one of those questions reality was never going to let us answer cleanly. A boundary built into the structure of existence itself, marking the edge of what creatures like us, evolved to track predators and seasons, were ever meant to fully comprehend. Either way, the chip is still there, sealed inside its cylinder of near absolute cold, in a quiet lab in Santa Barbara, holding inside its frozen circuitry an answer to a question most of humanity has not yet learned to ask.